Hello, welcome to this video on AS Physics, and we're going to do it on electric circuits, and it's based on some fiddling around that we did yesterday with cables in the lab, and the idea was to write down everything that we did and to talk a little bit about the theory behind it and to explain the things that we observed. This was done in an informal way without a particular graph plotting or absolute values being taken, and it was just a matter of comparing what was happening as we connected different components in different arrangements. So those were all the arrangements that we tried. So let's have a little discussion about what happened. First thing that we did is that we connected a power supply, which here I've drawn as a battery, but it's just power supply, DC current, to a light bulb. In the formal circuit diagram, it should appear as the current circulating in this direction, since that's the positive side of the battery, even though the electrons are going in the opposite direction, as you should know. And when we did that, the light bulb was fine. It was connected and it was not it was in a good state, the light bulb, so it just lit. And you can talk about two things happening in this circuit very simply. One of them, you can put an ammeter here in series, and you can check that if you put it on this branch of the circuit or if you put it in this branch of the circuit, the current is the same, because it's just going around the loop, and Kirchhoff's law says that no current is lost. So that would happen if you would connect an ammeter to those 2 points. Similarly, if you take the potential difference across this light bulb, you'd have to connect your voltmeter across it, and then you would register the potential difference through the light bulb, which should be the same as the EMF of the DC power supply. Okay? So the EMF of that supply, or in this diagram it appears as a battery, would be the same as the potential drop through that light bulb. And that we explained with the pumping model, where if the water was being risen all this height by the EMF, then it would also have to drop exactly the same height on the way down as potential difference. And since in this case there's only one bulb, then all the potential difference needs to go through the one bulb. So if we set this guy here, the EMF in this guy here, to about 3 volts, say, then that potential drop through the light bulb should also register 3 volts, right? 3 volts of EMF, 3 volts for the light bulb, assuming there is no internal resistance. Now that is something we'll talk about later, but it's not a perfect assumption, and that's why we were really getting a difference between this reading and what the appliance was actually outputting as a voltage. So you get a little difference there. Okay, so that was our first circuit, very simple, and everything else we did was kind of a deviation from here. The second one we had a look at was very similar, but we connected in series to the light bulb a rheostat or variable resistor, and we had a look at what happens to the brightness of this light bulb here as we changed the resistance in this one. And the idea there was to understand how the EMF is then as a potential difference in the circuit, how it's then divided, how the division of it changes depending on the resistance of each particular component. So we put a voltmeter through both of them, both components. So I'm going to include here 1 voltmeter across a variable resistor, and we put another voltmeter across this light bulb. And then we also connected a voltmeter for the whole of the circuit, so that you can do here or you can do here at the bottom. There's 2 ways of drawing it. It's exactly the same thing. You can do this. Or you can do this. Okay, it's the same way of connecting it. Both are connecting it to the two sides of the wire. So I'm going to draw it at the top for simplicity. So what did we notice? Well, the EMF provided by the battery, what it does is that it elevates the potential energy per coulomb of the electrons of the charge carrier. So if you imagine that it's water, it's like a pump that lifts the water up to the very top and then allows it to drop. Now, if the water is being lifted this amount, then it's only going to be able to fall the same amount before it gets to the very same place where it started, right? Down here. So that's how much energy it's going to have, that potential energy, and it's the same with electric charge. However much EMF the battery has, that's how much it's going to drop through these two guys added together, right? So if this is 40 volts, that will be, this plus this will be 40 volts. Why? Because that's the two drops. There's one drop from here to here, through the first component, which is a battery, and there is a second drop through here through the second component, which is a variable resistor. So those two drops together have to add up to the EMF. So we cranked the supply to different voltages, and say we put it up to 5 volts, so that was the EMF being produced. Then we noticed that the reading in this voltmeter plus the reading in this voltmeter was adding also to 5 volts. So whatever this was, if this was 1 volt, then this would have had to be 4 volts. Okay, now what we noticed as a second thing, which is really the reason why we chose to use a variable resistor, was that when we change this resistance here, the moment we increase the resistance, so if this R here we put it up, what happened was this potential drop was bigger. This potential drop here was bigger than this one, or it was just increasing. And as this potential drop here was increasing, this light here was becoming less bright. So I hope that makes sense, that if the current is going in this direction, the first component that it's going to go through is the light bulb. And so I've given it here just 1 volt because I just talked about this resistance being increased. And if I crank this guy up enough, this voltmeter here will start going up and up and up. Why? Because the bigger the resistance, the bigger the resistance of a component, the larger the potential drop through it. And the reason is, you can think of the potential drop in energy, so the voltage across it, potential drop is the energy that the electrons lose as they go through the component, and a component with a large resistance is going to be a lot harder for the electrons to get through. So as they go through this component, they're going to drop a lot in energy. They're going to drop a lot in their potential energy. Therefore, this potential difference is going to register a larger voltage, the bigger the resistance of the component. So as we increase the resistance, this guy is going to get bigger, this second voltage here is going to get bigger, and this one is going to compensate, it's going to get smaller, because together they must always add up to the total of 5, which is what the battery is outputting. Okay, that we checked with this circuit, and it was happening. As this voltmeter here was rising, this guy was decreasing. Okay, so a question in an exam might ask you that. Explain why this voltmeter here is increasing as we increase the resistance, while the light is becoming less and less bright. Well, if this voltmeter is decreasing, it means the potential difference between here and here is smaller. So this poor light bulb, whose power, the formula for the power, which is the brightness of the light bulb, is current times voltage. If the voltage is going down, the power is going to go down. Why? Because the current is a constant. Okay, the current is not changing at all. This is a fixed EMF of 5 that we're putting through, so the current is going to be the same until we start changing the resistance here. But the fact is that this guy is going to get less and less voltage, and so he's going to get less and less shiny, as this is stealing more of the potential difference. So in other words, in a series circuit, the potential is shared between all the components that are in series. It is shared. While the current is not shared. The current is the same for everyone, so you don't have to share it. It's like not used up at all. But the potential difference is shared, okay, in a series circuit. So let's go to the next circuit, in which we have a slightly different situation, but also in a series circuit. And I only wanted to talk about this for a moment because the setup is pretty much the same as above, but instead of having a normal light bulb here, we put a piece of graphite, and a piece of graphite is just a resistor because it's not a very good conductor. And what we noticed is that we were fiddling around with this resistance, but basically what we noticed is that after a very short amount of time, I asked my students to disconnect the graphite and to pass me the rod, and they all were quite surprised to notice that this was incredibly hot very quickly. It gets hot very quickly, and that happens, and you got to know why it happens and to be able to explain it in a sentence in an exam. And if they say explain why the temperature of the graphite is increasing, that's because as the electrons, as the charge carriers, or as the electrons travel through the graphite or whatever material, through the material, they interact or they collide. Okay, collide. It's a kind of collision, electrostatic collision, with the atoms in the crystal. Thereby increasing their vibrations or vibrational energy. It's even better. Vibrational energy, which is in turn going to cause a rise in temperature, because that's what temperature is the average of the vibrational energy. Okay, so that's better if you understand it, so you don't have to remember it word by word. You can explain it in your own. Okay, so I was just explaining that the best thing with these is to understand the way that it works and to have an idea of why it happens like that. But the key words are what is important to remember. So you can remember interact and collide, either one you can say. You can remember the atoms in the crystal, that's another key word, thereby increasing their vibrational energy, which raises the temperature. Those are all the key words for explaining why the graphite gets hotter. Now this explains why anything heats up. Okay, any conductor will heat up slightly, but the difference is that very good conductors do not have so many collisions or interactions with the electrons that go through, because the way that the crystal is laid out, the electrons can get through without interacting so much. So a very good conductor will not heat up so much. But a graphite rod or any kind of resistor is laid out in such a way that there is a lot more collisions, and that's why we call it a resistor. It's very good at resisting the passage of current going through, but as a result it will heat up. Okay, and in a sense that's the job of a light bulb. The reason why this thing here shines is because it's got a very thin filament with relatively high resistance, made of tungsten, the metal, and the current is going through fat wires with very little resistance, and suddenly it tries to get through a very thin wire with a high resistance, and then what it does is that it heats it up a lot, and so that heat causes the tungsten to then emit a lot of light. Okay, so That's why with resistors these guys get hot a lot quicker than with the normal materials. Now let's go to the same setup that we had here. We're going to talk about it now, but with a parallel circuit instead of a series circuit. And to understand the difference between how the voltage, the potential difference, and the current is distributed in this circuit compared to the other one. Okay, so just a quick recap. Here we had current the same throughout the whole circuit all the time, and the voltage was being shared between these two in such a way that they always add up to this EMF. In this one here, what's happening is different. Current is still going in the same direction, but when the current gets here, it's going to split, and so we always label these in two ways, okay, I2 or I1 and I2, whichever way around, doesn't matter. And the idea here is to remember that Kirchhoff's laws say that whatever this is, okay, so this I here has to give you the sum of the other two, so that will be I1 plus I2, okay, and that means there's no charge lost, and the flow of current coming in is the same as the flow of current coming out. So this I here will split in two, and this equation needs to be satisfied. So please remember that, because that will be your way of checking if when you've calculated this and that, they add up to this. That will be your way of if you've done the right thing or if you made a mistake. Now, the current divides. So that's completely different from here. The current here did not divide, it just went through every single conductor. So that's the first difference, that the current divides. The second one, we noticed when we put voltmeters through each of the components. So what we did was we connected a voltmeter here, and we connected a voltmeter here, right? And to check if this thing with the currents was true, you just need to put an ammeter here, and put an ammeter there, and put an ammeter here, for example, and then you're measuring the current through this branch, and you're measuring the current through that branch, and you're checking if they add up to this branch, which they should. So that's with the ammeters. That would be easy enough to do, but with the voltmeters, what we noticed was that if you connected them in this way, if this was outputting an EMF again of like 5 volts, what we noticed was that this was reading also very close to 5 volts, not quite because there's some internal resistance here, but this was reading the same amount as this here. So it might have been reading a little bit less, but exactly the same voltage was reading in this, potential difference was reading in this voltmeter as it was reading on this one here. And the best way of explaining that is also with the model of the water. So if I'm increasing the energy of water by this amount, by 5 volts of EMF, then when the water falls, because a parallel circuit has two separate branches for the water to lose its energy, or the electricity to lose its energy, here's one branch, here's the other branch, those two branches end up back down here, which is the home cable at the end. They get back home. This is the end. This is one path for one of the roots, and this is the other. Through those two roots, they must lose all of the energy that they have. So both of those has to be a fall of 5 volts. Hope that makes sense. They've got to drop by the same amount. So both voltmeters will read exactly the same thing. It's different only when you have two bulbs here and you have one here. If you have two drops and one drop, then the total drop through here is going to be the same as the total drop through there. But each individual drop here will be obviously different to the one here, because there's two drops happening here and there's only one there. But the total drop through each one of those two branches is going to be exactly the same, for the reason that we just gave here with the drops. Okay, so both of these drops will be 5 volts. In other words, the voltage is not shared in a parallel circuit. They both get exactly as much as is available, both branches, so it's not shared. Okay, if we do want to share voltage in a parallel circuit, you would have to connect something here in series with this, and now you have two things in series. Now the potential difference shares. But if you only have two, or a million components all connected in parallel, they do not share the potential difference. That's one of the reasons why this battery will go flat a lot quicker than this one. Okay, because it's putting the same energy to both of them. So over time it will go flatter quicker when you connect things in parallel. So I hope that makes sense. And the other thing we observed was this brightness here. If you have this light bulb shining away and you start changing this resistance, what will happen is, if you increase the resistance in here, what will be affected is this guy here, the current. Okay, if you increase this resistance, this current will be smaller because it's having a harder time to go through, so the current's going to prefer to go through this route, right? So it's going to go through this one a lot more than through this one. So you should see in that case that this brightness is going to increase, because it's still got the same voltage as before, it's still got 5 volts, but it's now got a bigger current. So increase this resistance and this current will go up. Decrease this resistance and this shininess, the brightness of the bulb, will go down. Why? Because more of it is going to be going in this direction, less is going to be available to go through this one. And since power, which is the shininess of the bulb, will be energy per second, and that's power, is equal to current times voltage, and the voltage is staying the same, then current is going to be the boss in how bright this is. Okay, current goes up, it's going to be brighter. Current goes down, it's going to be less bright. So a question in an exam paper might ask you exactly that. It might say, an experimenter notices that if this resistance here goes up, this goes more shiny. Explain that. So the reason there would be resistance goes up, current in that branch goes down, I1, therefore I2 goes up, because total current, more of it is going to be going down through this branch, a lot more at the division here, and therefore if this goes up and voltage is still the same, P is equal to IV, so it's going to get bigger because this guy is getting bigger, so that's going to get more shiny. Okay, please try to follow that. If that didn't make a lot of sense, go back again just a little bit, like a couple of minutes, and play it, and hopefully it will make more sense. Okay, so it's all common sense if you understand what happens with current when you increase resistance, which is that current doesn't like resistance. Finally, a little mention of what happened here when we connected two light bulbs in series to another one here in parallel. So these two are connected in series to one another, but they're connected in parallel to this one. So an exam question could say, draw a circuit with 3 bulbs in series and one connected in parallel with those to those 3 in series. So then it would be, you draw your circuit, you draw 3 in series to each other, and then you have to draw 1 in parallel to those 3. So you would have another one here. Okay, and that would be your circuit. Okay, so that's how you would draw 3 bulbs in series connected to 1 in parallel. And what I've drawn here, what we did yesterday, is we connected 2 in series to 1 in parallel, and what we noticed was that the brightness of these 2 was lower than this one here. It's a lot lower, and the reason for that has been explained in the previous one, but I'll just go through it quickly again. If your current is going through the circuit, you have a total I here. If these 3 bulbs are all identical, what's going on is that the total resistance of this branch, you should know the resistances in series, you just add them, so let's call the resistance of each bulb R. The resistance then of this first branch is 2R, and the resistance of this second branch is 1R. So where's the current going to prefer to go through? Well, it's going to prefer to go through this one a lot more, twice as much as through this one, in fact, right? Because this one's got a lower resistance. So you can imagine this as being a very thin pipe, very hard to get through, and this being a fat pipe. So through the fat pipe the water is going to flow really easily, you're going to get a lot of water flowing, and through this one you're going to get less water flowing. That's why when these two currents divide, you're going to find that this current here is bigger, I2 is a lot bigger than I1. Okay? In fact, it's going to be exactly twice as big in this case. Now, the voltage, the potential difference, is the same through this guy, right, as it is through these two. It's the same. So because power is equal to IV, and this current is bigger, and this voltage is the same, this is going to be very bright. But because these two are sharing the voltage, not only are they sharing their own potential difference in 2, but also they're getting a smaller current to start with because they're offering a bigger resistance. So they're both going to have a smaller V and a smaller I. So actually I made a mistake before by saying that it was going to be, no, it's the brightness, that's okay. The brightness will not be twice as much here as there. But what I said about the currents is correct, it's going to be half as much. Okay, but the brightness is actually going to be affected more than the current, because the brightness is affected both by the change in current and by the change in voltage. And there's two things changing in that case. So the power is going to be affected more than the current. Hopefully that makes sense. So just to make that a little bit more clear, imagine it's not to do with the number of bulbs, it's to do with the resistance of each branch. So let's say you've got 3 bulbs in this branch. And let's say that here you only have 1 bulb. But this bulb's really big, it's got a very big resistance, so we're going to call this guy 4R. It's got 4 times resistance. And this guy has 1R, 1R, and 1R. What's going to happen in this circuit? Well, where is the bigger current going to flow? The current's going in this direction. When it gets through here, it's going to make a decision. It doesn't care how many bulbs are there. What it feels, what the current feels, is either an ease or a difficulty. The ease is going to come from the fact that it's got a low resistance. This total is going to be 3R, and this is going to be 4R. So the current here is going to go through here a bit less. It's going to less. So I2 is going to be smaller than I1, because here there's 3R and here there's 4R. So it's not to do with how many bulbs there are, it's to do with the combined resistance of that particular branch. Excuse me for the bell. Okay, so hopefully that made that clear. It's not about the number of bulbs, it's just the resistance. Okay, that's what's going to determine I. And if the question asks you about I, then that's the argument that you got to do. But if the question asks you about P, or the brightness, okay, P is power. And that's where the brightness comes from. The formula for power is current times voltage. And so if they ask you about brightness, you've got to talk about both things. You really got to talk about the current, and you've got to talk about the voltage. What's happening with each one? The voltage is the same through both branches. Through here, it's exactly the same as through here. It doesn't matter how many light bulbs, doesn't matter what the resistance is, the same potential difference is going to be dropped. Why? Because this wire is at the same energy and this wire is at the same energy. So the difference between those two wires is independent of what I put in the middle. I could put an elephant here in the middle. Now, if this guy is going to be the same in both cases, then what you can say is, because they have to share that same potential difference between 3 of them, the V through each of these is going to be smaller definitely than the V that's going across this one, because it's only 1, right? So these 3 V's are going to be smaller than this one here. That's definitely true. So that's already half the reason why these are going to be less bright. They're getting less V, therefore they're getting less P, and P is the brightness. The second reason is the I. Why are they getting less I or more I? In this case, they're going to get more I in the example that I've done, because this is 3R and that is 4R. So they're getting a slightly higher current even though they're getting a smaller V. Okay? Is it going to be less shiny or more shiny than this one? It completely depends on the numbers. Okay? Completely depends on the numbers in this case, because I've done it in such a way that they cancel each other out a little bit. But in this case here, it's very easy to understand, because in this case here the bulbs are the same resistance, all of them. So I'm going to draw it here again, because that diagram is already too messy. Here we had 2 bulbs, and here we had 1 bulb. And in this case, where all the bulbs are the same, very easy to understand what's going to happen to the brightness, because both the current is going to be less through this branch, because there's twice the resistance. I is going to be less than through here, and also the potential difference is going to be shared. So for both reasons, the power is going to be a lot lower in each of these bulbs than in that one. Okay, hopefully that helped with getting a few notions for what's going on in currents. And in the future videos, what we'll do is we'll do calculations, more sort of questions that you can get in an exam in terms of making or of calculating some numbers. This is all to get an intuition, and this is all fundamental in order to then do the calculations properly. You need to have these ideas in your mind. Thanks for taking the time to watch the video. I'll see you in the next one.